You know, a revolution doesn't always start with a huge explosion. Sometimes it starts with a tiny piece of silicon. Today, we're going to dive into the story of one of those pieces of tech, the Intel 8080 microprocessor. It's the little unassuming chip that really kickstarted the entire personal computer age.
So to really get the 8080 story, we have to start right here, with the machine that made it a star, the MIT's Altair 8800. As computer pioneer Harry Garland put it, this thing was the catalyst. This was the box that took computing out of these massive, cold, air-conditioned rooms and put it right into the hands of everyday people and hobbyists.
Right, so the Altair was the main event, the thing everyone was talking about. But what was really going on behind the scenes? What was that one key ingredient that made the whole thing even possible in the first place?
All right, let's set the scene. It's 1975. You're a tech hobbyist, and you walk by a newsstand, and bam! You see this on the cover of Popular Electronics magazine. This wasn't just another project. It was a promise. A real, honest-to-goodness mini computer that you could build yourself. The reaction was just electric.
And you know, the folks at the magazine, they knew they were sitting on something huge. They almost went with a pretty boring name, PE8, for Popular Electronics 8-bit. But someone, thankfully, said, no way, this is a stellar event, and so they named it Altair, after one of the brightest stars in the night sky. Kind of fitting for a machine that was about to launch a whole new universe of tech.
So what was the engine powering this new star? Well, it was the Intel 8080 microprocessor. The guy behind the Altair, Ed Roberts, he'd checked out other chips. The 4004, the 8008, just not powerful enough. The Motorola 6800, a beast, but it wasn't available yet. The 8080 was like the perfect Goldilocks chip. It was just right. But, and there's always a but, right? There was a pretty big catch.
And here it is. The catch was the price. A single 8080 chip back in '74 cost $360. I mean, think about that today. That's like over $2,000 for just the chip. A computer for regular people, at that price, it was pure fantasy. The math just didn't add up. No way.
But this is where the whole story pivots. Ed Roberts, he was a smart guy. He'd bought tons of calculator chips before, so he knew how to play the game. He goes to Intel, makes a deal, and gets the price down to $75. Just $75. That one deal, that was the game changer. All of a sudden, the dream of a personal computer, it was real.
Okay, so Roberts has the chip. The price is right. The revolution is on. But what made this little thing tick? What could it actually do? To really get it, we've got to look at it the way a programmer would have. So inside, the 8080 had the basics. Registers to crunch numbers, memory to store stuff, a program counter to know what to do next. But the real secret sauce, the thing that made programmers' eyes light up, was this thing called the stack pointer. This one feature opened up a whole new world. So what the heck is a stack? Well, the easiest way to think about it is like one of those plate dispensers in a cafeteria. The spring-loaded ones. It's just a temporary spot in memory to stash stuff. And this was a huge deal. Why? Because it meant a program could be in the middle of a task, pause, go handle something else, and then come right back to exactly where it was. That might sound simple, but it was the key to writing way more complicated software.
So, when a programmer wanted to save something, they would push it onto the stack, just like putting another plate on top of the pile. The chip would handle all the details of where it was stored. Super simple, super elegant. And then, when they needed that info back, they just pop it right off the top. Again, just like grabbing the top plate. This whole push and pop thing, it seems basic, but it was the system that let programmers write cleaner, more powerful code for these brand new machines.
But here's the thing you have to understand. The Altair, with its 8080 brain, wasn't just a product. It was more like a seed. And from that one seed, an entire ecosystem just exploded into existence. Hardware, software, brand new companies.
This was absolutely brilliant. Ed Roberts didn't make a sealed box. He built the Altair with this expansion system, a bunch of 100-pin connectors. They called it the S100 bus. And what it really was an open invitation. It was him saying, hey, come build stuff for my computer. And people did. They made memory cards, video cards, all sorts of things. It became the very first industry standard, and it's a perfect lesson. Open systems are what really light the fire of innovation.
And you know what happens when something is a hit? Right! Competition pops up.
Not even a year later, boom, the IMSA 8080 shows up. It had the same Intel 8080 chip, it used the same S100 bus, but they'd actually improved on the design. It was easier to build, had more room for expansion, and just like that, the personal computer race had officially begun.
Of course, a box of circuits is just a box of circuits without software, and the first real, useful programming language for the Altair became from these two college-age kids, Bill Gates and Paul Allen. They created something called Altair Basic, and that little program, well, that was the very first product from a tiny little startup they called Microsoft. Pretty wild, right?
So let's just step back and connect the dots. How does this one little chip, in a kit you bought through the mail, become the granddaddy of basically every processor for the next 20 years? The jump in power is it's mind-blowing.
I mean, just look at these numbers. You start with the 8080 and it's 6,000 transistors. That evolves into the 8086, the chip in the first IBM PC. Then you get the 286, the 386, and before you know it, you're at the Pentium with over 3 million transistors. It's a direct family line, a straight shot from that little Altair chip to the processors that absolutely defined the PC revolution. It's just an incredible explosion of computing power, and it all started right there.
So what's the takeaway? The story of the 8080 is the perfect example of how the right piece of tech, at a price people can actually afford, at just the right moment in time, can literally change the world. It really makes you think, doesn't it? What's out there right now? What's the next 8080? What's that one little thing that's about to kick off the next big revolution?
You know, when you look at this tiny piece of silicon, the Intel 8080, it's easy to just see an old computer chip. But this is so much more. This is the spark that literally ignited the personal computer revolution. So today, we're going to peel back the layers and see exactly how its internal design changed the world. Okay, picture this. It's April 1974, and Intel drops this thing on the world. A complete 8-bit central processing unit, all on one little chip. I mean, before the 8080, computers were these massive, room-sized, super expensive behemoths. But this chip, it packed enough processing power into an affordable package to become the brain of early PCs like the legendary Altair 8800. It basically shrank the computer from a whole room right down to a desktop. And just look at the incredible pace of innovation here. In just 2 years, Intel jumped from the 8008 to the 8080, nearly doubling the transistor count. But the real game changer was the address bus. It expanded from 14 to 16 bits. Now that might not sound like a huge deal, but it meant the 8080 could manage 4 times more memory. That was a massive leap, and it unlocked the potential for way more complex and powerful software. So to really get what made the 8080s so special, we're going to go on a grand tour of its internal architecture. We'll start with the big picture, the overall anatomy, then we'll zoom in on the key parts, the arithmetic logic unit, the registers, the control section, and finally, how it all plugs into the outside world. All right, every great journey needs a map, and for our tour inside the 8080, our map is the chip's own functional block diagram. Think of it as the blueprint that shows how all the different pieces fit together to make a working digital brain. Now, at first glance, this diagram, it looks like a complex web of boxes and lines, and, well, it is. But don't worry, we're going to break it all down. This is basically an X-ray of the 8080, showing us all the core components that have to work together to execute every single command. Intel's own documentation breaks this whole complex blueprint down into 4 main sections. We've got the registers, which are like the CPU's short-term memory. We've got the ALU, which is its calculator. There's the control section, kind of like its conductor. And then the data bus buffer, which is its communications port. Let's kick things off with the calculator. So every CPU needs a core that does the actual math and decision-making. In the 8080, and really in every processor since, that part is the arithmetic logic unit, or ALU for short. This is the real computational heart of the chip. The ALU is basically where the chip does its thinking. Anytime a program needs to add 2 numbers, or compare 2 values, or do some kind of logical operation, the control unit sends the data right here to the ALU to get the job done. It's the engine that crunches all the numbers. Diving a little deeper into the ALU, the most important piece is the accumulator. It's an 8-bit register that's kind of like the main display on a calculator. It holds a number for an operation, and then it stores the result. It's helped out by some temporary registers for stuff in the middle of a calculation, and a super important flag register. This little guy keeps track of the outcome, telling the CPU things like, hey, the result was 0, or that calculation was too big and you carried over a digit, just like we did in grade school math. Okay, so for the ALU to work its magic, it needs a super fast place to store the data it's working on at that very moment. And that place is the register array. You can think of it as the CPU's own personal scratchpad or workbench. And this is the core of that workspace. On top of the accumulator we just talked about, the 8080 has 6 other general-purpose registers. Programmers could use these to stash values and shuffle data around at absolutely blistering speeds, way faster than going out to the main computer memory. Now, among all the registers, 2 of them are absolutely vital for managing how a program runs. The first one is the program counter. The best way to think about it is as a bookmark. It is always pointing to the exact spot in memory where the CPU is going to find its next command. Once it fetches an instruction, it automatically clicks forward, making sure the program runs step by step. The second crucial manager is the stack pointer. This register looks after a special part of memory called the stack. The stack works just like a stack of plates. You can push new things onto the top or pop things off. The CPU uses this to temporarily save where it is and what it's doing when it gets interrupted or needs to run a little side program. It allows it to jump away, do something else, and then come back to the exact spot it left off. So we've got the calculator, the ALU, and the workspace, the registers. But what tells them what to do and when to do it? Well, that's the job of the control section. If the CPU is an orchestra, the control section is the conductor, waving the baton and making sure every single part plays in perfect harmony. This block is the director of the whole show. It grabs the next instruction from memory, using the address that the program counter is pointing to. Then, it decodes that instruction to figure out what it means. Is it telling it to add? To move data? Based on that answer, it shoots out these perfectly timed electrical signals that turn on the ALU, the registers, and the buses to carry out the command. This fundamental process is called the fetch, decode, execute cycle, and it is the heartbeat of every computer ever made. The 8080 just does this cycle over and over again, millions of times per second. Fetch a command, decode its meaning, and then execute it by lighting up all the right internal parts. This simple, relentless loop is what turns a boring list of instructions into a program that actually runs. We've now toured all the major internal blocks. But, a brain is pretty useless if it can't communicate. So the final piece of our puzzle is how the 8080 actually talks to the rest of the computer, the memory, the keyboard, the screen. It does this using buses, which are basically information highways. The 8080 uses 2 main highways. First, there's the 16-bit address bus. This is a one-way street. The CPU uses it to send out a specific memory location. It's basically shouting, "Hey, I need to access this address." Then you have the 8-bit data bus. This one's a 2-way street. Once the address is picked, the actual byte of information travels along this bus, either going into or coming out of the CPU. And this is how those abstract highways become a physical reality. Each one of the 40 pins on this chip has a very specific job. You can actually see the pins labeled A0 through A15 for that 16-bit address bus, and D0 through D7 for the 8-bit data bus. This is it. This is the chip's physical connection to the rest of the world. So we've seen the calculator, the workspace, the conductor, and the highways. And on their own, they seemed like fairly simple building blocks, right? So what was the magic here? How did this specific combination of components, all on a single chip, manage to completely change the world? Well, the answer is that the 880 wasn't just another component. It was a complete system orchestrator. It could act as a master CPU, directly managing memory and all the input and output devices. It had everything it needed to be the single controlling hub of a general-purpose computer. And that's really what it comes down to. The revolution wasn't about any single feature. It was about the integration. By successfully cramming the ALU, the registers, the control logic, and all the bus interfaces onto one reliable, affordable piece of silicon, Intel didn't just create a new processor. They created the very possibility of the personal computer, proving that an entire digital brain could live on a single chip. It really makes you wonder, what's going to be the next single piece of tech that changes everything?
All right, let's get right into it. Today, we are going to crack open one of the most legendary chips ever made, the Intel 8080. And we're not just looking at the outside. We are zooming way in to its absolute core, the part that does all the real thinking, the arithmetic and logic unit, or as you'll hear me call it, the ALU.
And here it is, the legend itself. This little guy, released back in the mid-70s, was the brain powering some of the very first personal computers, like the famous Altair 8800. I mean, this was a complete central processor on one single piece of silicon. For its time, that was an absolute game changer.
So here's how we're going to break this down. We're going to start big picture, looking at the 8080 as the brain of the machine. Then we'll peek inside the CPU's architecture. From there, we'll put its core calculator, the ALU, right under the microscope. We'll see how it does the math, how it thinks with logic, and finally, how it keeps track of everything with flags. Sound good? Let's jump in.
First up, the brain of the machine. And you have to understand, the 8080 wasn't just a component. In many ways, it was the component. It was the central hub that controlled everything, from memory to peripherals, basically making the whole idea of a personal computer even possible. And to get a feel for what a marvel this was back in 1974, just think about this. Intel managed to cram 6,000 transistors onto this thing. Now, I know what you're thinking. Today's CPUs have billions, which is just staggering. But back then, those 6,000 transistors were more than enough to spark a revolution.
Okay, so we've seen the 10,000-foot view. Now, it's time to pop the hood and see what's actually going on inside, to look at the functional blocks that really make this processor tick.
This right here is our map, taken straight from the original 8080 datasheet. It looks complex, but you can see all the different sections working together. You've got the register array over here for storage, the control section directing all the traffic, and right there, in the middle of it all, that's our target for today, the arithmetic and logic unit.
So, the datasheet basically boils the 8080 down into these 4 key areas. And look, they're all super important, but the one that does all the heavy lifting, the part where data isn't just stored or moved around but is actually changed, well, that's the ALU. It's the real engine room of the whole operation.
So let's zoom in on that engine room, the core calculator. If the entire CPU is the brain, you can think of the ALU as the part that's doing the active thinking. It's performing the calculations and making the critical decisions.
You know, the official user manual actually puts it perfectly. It's the part of the CPU hardware that performs arithmetic and logical operations on binary data. It sounds so simple, right? But those two things, arithmetic and logic, are the foundation for literally everything a computer does. So, what's actually in this engine room? Well, it's mostly a handful of specialized, super fast storage spots called registers. You've got the accumulator, which is like its main workbench. You've got some temporary registers, which are kind of like a scratchpad for jotting down numbers. And then you have the flag register, which is like a set of little sticky notes for keeping track of the results.
Okay, theory is great, but let's actually see this workbench in action. We'll start with the A in ALU, arithmetic. This is all about good old-fashioned number crunching. Now, to get the ALU to do anything, you have to give it an instruction. Here's a total classic, add M. It's a simple command, and all it's really saying is, hey processor, go grab a number from memory, add it to whatever's already on the workbench, the accumulator, and then put the final answer right back on the workbench.
So let's walk through it. Step 1, the CPU grabs a number from memory. Step 2, the ALU gets to work and adds that number to what's in the accumulator. Step 3, that new result replaces the old one. And finally, and this part is absolutely crucial, those sticky notes, the flags, get updated to tell the story of what just happened. Was the result 0? Did we have to carry the 1? The flags tell us everything we need to know.
But the ALU is not just a glorified calculator. It can also think, using logic. This is the L in ALU. And trust me, it is every bit as important as the arithmetic.
Now check out a logical instruction, ANM. This tells the ALU to perform a logical AND. Instead of adding numbers together, it compares their individual bits. It's kind of like a bouncer at a club checking 2 forms of ID. Only if both IDs are valid, or in this case, if both bits are a 1, does it let you through. This incredibly simple comparison is the foundation for all decision-making in a computer.
So that's the key difference, right? An arithmetic ADD combines the whole values. A logical AND is more like a microscope looking at each pair of bits one by one. If both are 1, the result is 1. Otherwise, it's 0. One is for calculating, the other is for testing and deciding. The ALU has to be a master of both. And that brings us to that final piece of the puzzle, the flags. Because after every single operation, whether it's math or logic, the ALU needs a way to report back on what happened. And that's exactly what the flags are for.
And the datasheet tells us exactly how many there are. 5 main condition flags. The easiest way to think of them is just as 5 little status lights that the rest of the processor can check at any time.
Each of these 5 flags tells a simple but incredibly important story.
The 0 flag gets flipped on if a result is exactly 0. Why is that useful? It lets a program ask, hey, have we reached the end of our countdown yet? The sign flag tells us if a result is negative, perfect for checking if a video game character's health has dropped below 0. Parity is a basic error check, and the carry flags tell us if a calculation got too big for its 8-bit box, kind of like when your calculator runs out of digits. These simple on or off signals are the building blocks of all complex if-then logic in software.
And when you zoom all the way back out, that's the truly mind-blowing takeaway. Every app on your phone, every website, every piece of complex software is at its absolute lowest level, just built on millions upon millions of these incredibly simple arithmetic and logical operations with these little flags keeping score. It all starts right here, inside the ALU. And it makes you wonder, how do these simple, tiny building blocks create the immense digital world we live in today?
All right, today we're going to dive deep right into the silicon heart of a computer. We're going to tackle a question that sounds super simple, but you'll see it reveals the very foundation of how all computers actually, well, think. So how does a computer really add two numbers? And I mean, really, at the most basic fundamental level, what is actually going on in there? It seems so obvious, but the answer is where all the magic is. It reveals the brilliant design at the core of all computing. You know, it all happens inside the computer's brain, the central processing unit, the CPU. Think of it as this tiny engine that does all the real work. And for our journey today, we're going to use this amazing original diagram of the legendary Intel 8080 microprocessor as our map. This is the chip that basically powered the first wave of personal computers. So let's pop the hood, shall we? Let's take a look inside that CPU's engine. Okay, our first stop is the arithmetic and logic unit, or ALU for short. This is the real number cruncher of the whole operation. If the CPU is the brain, the ALU is that specialized part that does all the heavy lifting, all the math like addition and all the logical stuff like figuring out if one number is bigger than another. But here's the thing, the ALU can't just work in a vacuum. It needs a dedicated place to hold and work with data. And that, my friends, brings us to the star of our show today, the accumulator. Think of it as a very special workbench. So what is this thing? Well, the accumulator is a special 8-bit register. And register is just a fancy word for a small, high-speed storage spot right there inside the CPU. Its job is simple, but it's crucial. First, it holds one of the numbers being worked on, that's called an operand, before the calculation. And second, it stores the final result after the calculation is all done. The best way, really, the only way to picture this is as the ALU's main workbench. It's the one dedicated spot where a number is placed, gets worked on by all the ALU's tools, and then where the finished product is left for the next step. It is truly central to the entire process. And it's not working alone. The accumulator is part of a small, super specialized team. It's got temporary registers helping it hold data in the middle of a calculation. And there's this special flag register that keeps track of important results, like, hey, did that last addition end up as 0? Okay, so theory is great, but let's see this thing in action. We're going to trace one single command from the very beginning to the very end. Let's follow the story of a simple addition. Now, this line of code, it might look a little cryptic, I get it, but this is the language the CPU actually speaks. It's an add immediate instruction, and what it's telling the CPU is this. Hey, take the value that's currently in the accumulator, that's the A, add the number you find in the next piece of this instruction, the second byte, and then store the new result right back into the accumulator. It's so simple, but so elegant.
And here's how that whole process breaks down. Let's just walk through it. Step 1, the CPU grabs the add command from memory. Step 2, it goes and gets the number it's supposed to add. Step 3, okay, now both the number already on the workbench in the accumulator and this new number are sent over to the ALU. Step 4, zap, the ALU does the actual math. And finally, step 5, the new sum is written right back onto the workbench, replacing whatever was there before. The whole thing is like this beautifully choreographed little dance of data.
And how long does this all take? For an old Intel 8080, this entire process, this whole dance, takes just 7 clock cycles. You can think of those as the fundamental heartbeats of the processor. We're talking about a few millionths of a second. It is an incredibly fast and efficient operation happening right there on the silicon. But hey, the accumulator is no one-trick pony, not at all. Addition is just the beginning. Let's take a look at the accumulator's many other jobs. So here's the crucial thing to get. This isn't just for adding numbers. The accumulator is the central hub for a huge range of the CPU's commands. I mean, almost every single arithmetic and logical operation pivots around this one special 8-bit register. I mean, just look at this. The sub command subtracts a value from the accumulator. The ORA command performs a logical ORA operation with the accumulator. You've even got instructions like RLC that don't even do math. They just rotate all the individual bits of data inside the accumulator. You see the pattern here? In every single case, the accumulator is right there at the center of the action. Okay, so let's zoom out a bit. Let's step back and appreciate the incredible, enduring legacy of this simple design. This accumulator-centric design was an absolute cornerstone of the 8-bit era. And it wasn't just a clever idea, it was kind of necessary. By focusing most of the action on a single register, designers could dramatically simplify the CPU's internal wiring, and that made chips like the Intel 8080 cheaper and way more reliable to produce. It literally defined how early personal computers thought. And the evolution from this 8-bit era was just lightning fast. The 8080 successor, the 16-bit 8086, was a massive leap forward. It could handle twice as much data at once, and the memory it could talk to just exploded from 64 kilobytes to a full megabyte. But even with these huge advances, those core design principles learned from the 8080, they carried forward.
Now, of course, the CPUs in our phones and laptops today are light years ahead in complexity. They have tons of general-purpose registers instead of relying so heavily on just one accumulator. But that fundamental principle, that idea of having a dedicated, super-fast workbench right next to the ALU, that idea absolutely lives on. It's a foundational concept of computer architecture.
So that kind of leaves us with a final thought, doesn't it? As computer architectures keep evolving at this absolutely incredible pace, how do these foundational ideas, the ones born in the 8-bit era, still shape the amazing devices that we use every single day? You ever stop and think about how your computer's brain actually juggles all that data? Well, today, we're going to crack open that black box. We're diving deep into one of the most fundamental parts of a CPU, the general-purpose register. And to do it, we're going to use an amazing piece of tech from way back in 1974 that pretty much started it all. It's a massive question, isn't it? We throw around words like processing and computing, but what's really going on under the hood? It's not magic, I promise. It's actually a beautifully elegant system for holding and messing with tiny bits of information at absolutely incredible speeds. So to get our answer, we're going back in time to this little guy, the Intel 8080. Now, it might look like something out of a museum, but I promise you the core ideas of how this thing works are still alive and well inside whatever device you're watching this on right now. This chip is our key. You see, the 8080 was a real pioneer. Its own datasheet called it a complete 8-bit parallel central processor unit, all on one piece of silicon. Think about that for a second. They crammed the entire brain of a computer onto one single component. That was a game changer. Okay, let's take a look at the blueprint. This is the functional block diagram of the 8080. And yeah, I know it looks super complicated, like a city map. This shows how data moves around, gets processed, and sent back out. But don't worry, we're not going to try to understand the whole thing. We're going to zoom in on the part that really matters for our story today. Right there. See that box labeled to register array? That's where we're headed. This is where the CPU does its most immediate hands-on work. Forget your hard drive, forget your RAM for just a second. This little spot is where the thinking, the actual work gets done. You know, the best way to wrap your head around this is with an analogy. If your computer's RAM is like a giant pantry, full of all your ingredients, then the registers, they're the chef's cutting board. It's a small, limited workspace, yeah, but it's where all the action happens. And it has to be incredibly fast. And that, right there, is exactly what a general-purpose register is. It's not for long-term storage, not for your photos or anything. It's an ultra-fast, temporary holding spot for the specific number or instruction the CPU needs right this very second. So the 8080 has 6 of these little workbenches, and they just gave them simple letter names: B, C, D, E, H, and L. Think of each one as a tiny little bucket, right? And each bucket can hold exactly one small chunk of data, an 8-bit chunk, to be specific. So what does 8-bit even mean? Well, it's just a number made up of 8 ones and zeros. With those 8 little slots, you can represent any whole number from 0 all the way up to 255. That's it. That's the biggest number a single one of these little buckets can hold. Okay, so that immediately brings up a problem, right? I mean, computers are constantly dealing with numbers way bigger than 255. And maybe even more importantly, to find things in memory, they need addresses. And you're going to need way more than 255 addresses. So how did an 8-bit system get around this? Well, the engineers who designed the 8080 came up with a really clever, really elegant solution. They just paired them up. And it wasn't random. There was a system to it. The B and C registers to team up, so could D and E and H and L. By snapping them together, they could act as one single 16-bit unit. It's kind of like one register holds the first half of a big number and the other one holds the second half. So you take two 8-bit registers, you stick them together, and you get a 16-bit space. Now, this simple trick doesn't just double the capacity. Oh no, it blows it up exponentially. And here's where you see just how huge that difference is. A single 8-bit register, it maxes out at 255. But a 16-bit register pair can hold a number all the way up to 65,535. And that is the magic number. That much larger number meant the 8080 could directly talk to 64 kilobytes of memory, which for 1974 was a ton of space. Okay, so that's the what. But what about the how? How does a programmer actually tell the CPU to use these registers? Well, they use a special set of commands, kind of like a secret language, called an instruction set. Here's what one of those commands looks like. LXI. H. I know, it looks a little cryptic, like alphabet soup, but it's a direct, no-nonsense order telling the CPU exactly what to do. Let's decode this. LXI is just short for Load Register Pair Immediate. The H tells the CPU which pair to use, in this case, the H and L team. Right after this command, the programmer puts a 16-bit number, and the CPU just grabs that number and plops it right onto its workbench, into the H and L registers. Simple as that. All right, let's look at one more. This one's cool. DAD-B. This shows that these pairs weren't just for holding stuff. They were for actually doing math with it. DAD stands for double add, which is just a great name for 16-bit addition, right? With this one command, the CPU takes the 16-bit number in the BC pair, adds it to the 16-bit number that's already in the HL pair, and then boom, it stores the sum right back into the HL pair. It's a super efficient way to handle bigger calculations in a single step. Now, it's easy to look at this stuff and think, okay, that's ancient history. I mean, the 8080 was built with just 6,000 transistors, but the foundational ideas it pioneered, man, they're anything but obsolete. Just look at this timeline. It's absolutely insane. We go from the 8060s, 6,000 transistors, to the Pentium's 3.1 million in less than 20 years. Everything got bigger, faster, way more powerful. But that core concept of general-purpose registers as the CPU's workbench, that stayed. The registers themselves got bigger. Sure, they went from 8-bit to 16, then 32, and now 64-bit, but the fundamental idea is exactly the same. You know, this quote from the original 8080 datasheet just nails it. The very features they were bragging about back then, the powerful instructions, the general-purpose registers, being able to talk to 64K of memory, these are the very things we just broke down. This stuff was revolutionary, and it absolutely set the stage for everything that came next. So the next time you hear about some brand new processor with billions of transistors and mind-blowing speeds, just remember the old 8080. Because deep down inside all that cutting-edge tech, that simple, beautiful idea of a tiny workbench is still in there, doing all the heavy lifting, one calculation at a time. It really makes you wonder, doesn't it? What other 50-year-old ideas are still hiding in plain sight, secretly running our world today?
Hey everyone and welcome. Today we're going to do something really cool. We're diving deep right into the silicone heart of a computer to pull back the curtain on this elegant secret, how a machine actually makes a decision. So let's get into it.
I mean, it really all comes down to this one big question, right? We see it happen a million times a day, computers reacting to what we do. But how does a hunk of metal and silicon decide to do this instead of that? It feels a little like magic, but I promise you, it's just a really, really brilliant piece of engineering.
And to really get our heads around it, we need to kind of hop in a time machine and meet the brain that kicked off the entire personal computer revolution.
Meet the Intel 8080. This little chip, released way back in 1974, was an absolute powerhouse for its time. It was the digital mind inside some of the very first personal computers, like the famous Altair 8800. For our story today, this chip, this is our hero.
So what was the 8080's big secret? You know, it wasn't some kind of futuristic AI. Nope.
The key to its ability to think is a surprisingly simple little component called the flag register. And this, right here, is where all the magic happens. So this flag register, what is it really? Well, it's basically just a small collection of tiny 1-bit switches, and the 8080 has 5 of these key switches that we call condition flags. Let's break down what each one actually does. Honestly, the best way to think about these flags is to picture a little dashboard with 5 indicator lights. Every single time the CPU does a calculation, adding, subtracting, whatever, these lights blink on or off to tell a very specific story about what just happened with that result. First up, we've got the most straightforward one of the bunch, the 0 flag, or Z for short. Its job? Super simple. If a calculation ends up with an answer of exactly 0, the 0 flag light turns on. In computer speak, that means it's set to 1. If the answer is anything else, literally anything, the light stays off, or reset to 0.
Let's see it in action. It's really simple. Over on the left, if the CPU calculates 10 minus 5, well, the answer is 5. That's not 0, so the 0 flag just stays off. But look at the right side. When it calculates 5 minus 5, the answer is exactly 0. And bam, the 0 flag instantly flips on. So simple, but as you'll see, so powerful.
Next up is the sign flag, or S. This one's job is to keep an eye on whether a result is positive or negative. In the 8-bit world of the 8080, the way it does this is by just looking at the very last bit of the number, what we call the most significant bit. If that specific bit is a 1, the computer treats the number as negative, and the sign flag gets set. Okay, so in an 8-bit number, you've got bits 0 through 7, right? The sign flag couldn't care less about the first 7 bits. It's only looking at that last one, bit 7. If an operation ends up with a 1 in that final spot, the S flag goes up. If it's a 0, the flag stays down. It's just a super fast, simple way for the CPU to check if a result is negative. All right, let's move on to one of the more interesting flags, the parity flag. This one's a little different. It doesn't care about the value of the result, it cares about its structure. The parity flag, P, just counts up the number of 1s in the binary result. If that number is even, the flag gets set. If it's odd, the flag is reset. It's actually an old-school method for doing a basic error check on data. Look at these 2 examples here. The number on top has 5 1s. That's an odd number, so the parity flag is off, telling us it has odd parity. The bottom number, though, has 4 1s, an even number, so that parity flag flips on to signal, you guessed it, even parity. Now for a flag that should feel pretty familiar from like elementary school math, the carry flag, or CY. You remember doing addition and having to carry the 1? Well, that's literally what this flag does. The 8080 works with 8-bit numbers, so if a calculation gives a result that's too big to fit in those 8 bits, that extra bit has to go somewhere. It carries over, and that sets this flag. And this slide shows it perfectly. We're adding 1 to the absolute largest possible 8-bit number. The result is a number that needs 9 bits. Well, the CPU's register can only hold 8. So that 9th bit kind of spills over, and in doing so, it sets the carry flag to 1. This is absolutely crucial for doing math with numbers bigger than the CPU can handle at once. And finally, we've got the super specialized auxiliary carry flag. Think of it like a little brother to the main carry flag. It only watches for one very specific thing, a carry from bit 3 over to bit 4. Its main job was to help the CPU handle a special format called binary coded decimal, which was pretty common way back when. Okay, so let's recap. We've got these 5 little indicator lights that tell us if a result was 0, negative, had even parity, or if it overflowed. That's all great information, but how does any of that actually become a decision? This is the absolute key to everything. The flags tell the story of what just happened. But how does the CPU read that story and then do something different because of it? How does it connect the information to an action? And here it is. This is the answer. This is the Rosetta Stone. The 8080's programming language has these special commands called conditional jumps. For example, there's an instruction JZ, which means jump if 0. This command tells the CPU, hey, go look at the 0 flag. If that flag is on, the program literally jumps to a totally different part of the code. If it's off, it just carries on to the next line. And as you can see, there's a jump for pretty much every condition. JNZ for not 0, JC for carry, JM for minus, and so on. So here's the bottom line, the whole point. The flags are the senses, and these conditional jumps are the actions. A program can subtract 2 numbers and then use a jump if 0 instruction to basically ask, hey, were those 2 numbers equal?
If the zero flag is on, the answer is yes, and the program can branch off and do something completely different. That right there is decision-making at its most fundamental level.
Now, I know what you might be thinking. Okay, this is neat history, but it's from a processor from the 1970s. What does this have to do with anything today? Well, the truth is, this idea has an incredibly powerful and lasting legacy.
See, the concept that chips like the 8080 introduced was so fundamental, so elegant, that it became the bedrock of processor design. It was expanded on in the 16-bit 8086 processor a few years later, and that architecture is the direct ancestor of the processors in all of our computers today. That core idea, do a math problem, set the flags, then make a choice with a conditional jump, is still happening billions of times every second inside the chip that's powering whatever device you're watching this on right now. So the next time you're playing a game and your character dodges an attack, or your spreadsheet instantly recalculates a massive formula, you'll know what's really going on under the hood. It isn't magic. It's just a series of incredibly fast, simple questions being asked about those tiny flickering status lights, a secret language of flags that for the first time turned a piece of silicon into a true decision-making machine. Thanks for watching.
All right, let's dive deep inside the brain of every computer. We're going to look at one of the most basic, most important parts of the whole system. It's basically an internal bookmark that makes sure everything, and I mean everything, runs the way it's supposed to, one tiny step at a time.
So think about it, right? A computer program, at its core, is just a massive list of instructions stored in memory. When a CPU is blazing through these, how does it always, without fail, know exactly which instruction comes next? We're talking millions, even billions of times a second. How does it never lose its place?
Well, the answer is a tiny but absolutely critical piece of hardware called the program counter, or PC for short, and honestly the name says it all. It's a special little spot of memory, a register, right on the CPU. Its whole job is to hold the memory address of the next thing to do. It's just like sticking a bookmark in a book to remember your page. It's that simple and that powerful.
Now, to really wrap our heads around this, we're not going to start with some super complex modern chip. Nope, we're going to take a trip back in time to an absolute legend, the Intel 8080 microprocessor from 1974. Its design is just so clean and influential, it's the perfect way to see how this all works.
And check this out. This isn't just some abstract idea. Here's the actual block diagram for the 8080. You can literally see the program counter right there, a real physical piece of circuitry connected to everything else. It's a tangible part of the chip's design.
For the Intel 8080, the program counter is 16 bits wide. And that one number, 16, is maybe the single most important detail about this entire processor. It basically defines the size of its entire universe, as you're about to see.
So why is 16 bits such a huge deal? Well, a 16-bit number can represent 2 to the power of 16, which is 65,536 different values. That means the 8080's bookmark can point to any one of those spots in memory. And that's the key takeaway. The size of the program counter directly limits the maximum amount of memory the CPU can talk to. In this case, 64 kilobytes. That was its whole world.
Okay, so the program counter is pointing to an instruction. What happens next? Well, most of the time, its job is incredibly simple. It just moves forward, one step, then another, and another. This is the fundamental rhythm of every CPU, the beat it marches to. First, it uses the address in the program counter to fetch an instruction from memory. Then, and this is so important, it immediately increments the program counter to point to the next address. And only then, third, does it actually execute the instruction it just grabbed. It's always thinking one step ahead. And hey, don't just take my word for it, let's go straight to the source. The original Intel 8080 user's manual spells it out perfectly. The processor just adds 1 every single time, keeping that bookmark moving forward through the book. This is the CPU's default setting. Just keep on trucking.
But let's be real. Programs aren't that simple. You don't just read a book from cover to cover every time. Sometimes you need to skip a few chapters, or maybe you need to go back and reread a critical section. Programs need to make choices, and that's where the program counter gets really interesting.
Just look at the difference here. On the left, you've got that normal, steady +1+1 flow, but on the right, you have branching. This is where a special jump instruction comes in. Its only job is to tell the CPU, hey, forget what's next, I want you to load this brand new address into the program counter. It's like grabbing the bookmark and slamming it down on a totally different page.
And this, right here, is the building block of all software logic. A jump can be unconditional, like always go here, no matter what. Or it can be conditional. Check the result of that last math problem. If the answer was 0, then jump over here. If not, just carry on. That's how your if-then statements and all your loops work, way down at the hardware level.
The 8080 actually has a really cool instruction that shows exactly how this works. It's called PCHL. All it does is take the 16-bit number stored in two other registers, H and L, and just copies it straight into the program counter. The second that happens, boom. The very next instruction the CPU fetches is from that brand new location. The program's path is changed in an instant.
Okay, so we can jump to a new spot. That's cool. But what if we need to jump, do some work over there, and then come back to exactly where we left off? This is something programs do constantly with things called subroutines.
This is handled by a special kind of jump, called a call. You could think of a subroutine as a reusable piece of code. Instead of writing it out a dozen times, you just call it when you need it. But how in the world does the CPU remember how to get back?
It uses a clever trick with another register called the stack pointer, which manages a special area in memory called the stack. The easiest way to think about the stack is like a pile of plates. You can only put a new plate on top, and you can only take the top plate off. Last one on is the first one off.
So here's the elegant part. When a program executes a call, the CPU first takes its current bookmark, the address of where it needs to return, and pushes it onto the top of the stack for safekeeping. Then it jumps to the subroutine. When the subroutine's all done, a return instruction tells the CPU to pop that saved address right off the stack and put it back into the program counter. And just like magic, the program picks up right where it left off.
And what's really cool is this same push and pop system is what lets the CPU handle things like you pressing a key on your keyboard. That's an interrupt. An external device basically taps the CPU on the shoulder, forces a special kind of call, and the CPU saves its place on the stack, goes and deals with the keyboard, and then returns to its original task without missing a beat.
So we've seen that the program counter is so much more than a simple counter. It's the master navigator, right? It lets us go step by step, it lets us make decisions, and it lets us call reusable code. But its importance, it goes even deeper.
Just look at this chart. Only 4 years after the 8080, Intel came out with the 8086. The single biggest change was that the address bus grew from 16 to 20 bits. Now, that meant the program counter also had to get bigger. And that seemingly small change of just 4 more bits, it didn't just add a little memory, it blew the doors open, from 64 kilobytes all the way up to a full megabyte. That is a 16 times increase.
And that's the final crucial takeaway. The size of the program counter is not just some tech spec, it is a fundamental boundary. It sets the absolute hard limit on how much memory a processor can see and talk to. If you want a bigger world for your programs to live in, you need a bigger bookmark.
Which leads to one last thought. We started with the 16-bit program counter of the 8080, able to find its way to about 65,000 different places. The computer you're watching this on right now is almost certainly 64-bit. Its program counter, its bookmark, can point to over 18 quintillion different memory locations. It's an astronomical number. So the next time your computer is juggling a dozen different apps flawlessly, just take a second to remember the humble program counter, that internal bookmark that started it all, relentlessly pointing the way, one instruction at a time.
All right, today we are pulling back the curtain on a true unsung hero inside your computer's processor, the stack pointer. It's one of those deceptively simple ideas that solves a massive problem. And honestly, without it, the software we use every single day just wouldn't work. So let's just dive right in with the core problem. Imagine a program is chugging along, doing its thing, and it needs to jump over to a smaller, reusable piece of code, a subroutine, to get something done. The big question is, once it's finished, how in the world does it find its way back to the exact spot it left off? That's the puzzle we're going to solve. So here's how we're going to break it down. First, we'll really get a handle on the problem programs we're facing. Then we'll introduce the brilliant solution, the memory stack. From there, we'll look at a classic real-world example in the Intel 8080 chip, see how it all works under the hood, and finally, we'll understand why this whole concept was such a complete game changer. All right, first up, the memory problem. You can think of a running program like a long road trip. A subroutine is like taking a detour to see a cool landmark. But to get back on the main highway, you have to remember exactly which exit you took. You see, inside the CPU, there's a special register called the program counter, and its job is to always point to the very next instruction to be executed. When you call a subroutine, you have to change the program counter to point to that new piece of code. But wait, that means you've just overwritten the address you need to get back to. So where do you stash that return address so you don't get hopelessly lost? And that, my friends, brings us to the solution. An incredibly clever yet simple data structure that solved this problem and so many more. The memory stack. You know, the easiest way to get your head around a stack is the good old stack of plates analogy. It's simple. You can only add a new plate to the top of the stack, and you can only take a plate from the top. So, the very last plate you put on is always the very first one you take off. It's a simple rule, but it's absolutely key. And that whole last on, first off rule? Well, it's got a technical name. Last in, first out, or LIFO for short. This is the fundamental, unbreakable law of the memory stack. It means that the very last piece of data you save, like that critical return address, is guaranteed to be the very first one you get back. Now, this is a fantastic quote because it gives us a peek into the minds of these early computer architects. They had this brilliant idea. Let's put the program at the bottom of memory and let it grow up, and we'll put the stack at the very top of memory and let it grow down. I mean, how smart is that? It's an elegant way to make sure the two don't run into each other until you've used every last byte of memory. Okay, so let's get into the nitty-gritty and meet the real hero of our story, the specific piece of hardware that manages this stack inside one of the most important microprocessors ever made, the Intel 8080. Okay, feast your eyes on this, the Intel 8080. When this came out in 1974, it was a revolution. And one of its most important features was a 16-bit address bus. That meant it could access 64 kilobytes of memory, which was a ton back then. And that number, 16 bits, that's the magic number. It is the key to this whole thing. And here is exactly why that matters. Tucked away inside the 8080 is a dedicated 16-bit register called the stack pointer, or SP. Its one and only job is to hold the memory address of the current top of the stack. And of course, it's 16 bits. That's no accident. That means it's perfectly sized to hold an address that can point to any single byte in the 8080's entire memory map. Okay, so remember that quote about the stack running downhill? This is where the rubber meets the road. When you add data onto the stack, an operation we call a push, the address value in the stack pointer actually goes down. It feels a little backward at first, but it just means the top of the stack is always at a lower memory address. Let's actually watch this happen. So before the push, our stack pointer is sitting at address 13A6. We push a 2-byte value onto the stack, and look what happens. The data gets stored, and the new top of the stack, where the SP is now pointing, is 13A4. The address literally went down by 2. And you guessed it, the pop operation is the perfect mirror image of this. We start with the stack pointer at 1508. When we pop the data, we grab those 2 bytes, and then the SP gets incremented by 2, moving back up to 1508. The stack is literally shrinking upwards in memory. All right, we've got the big picture. Now let's zoom in on the 4 key instructions that actually make the stack pointer do its dance. Up first, the push instruction. This is what the CPU uses to put a 16-bit value on the stack. It neatly tucks the 2 bytes of data away in memory and then, crucially, moves the stack pointer down by 2, so it's pointing at the new top. And on the flip side, you've got the pop instruction. It's the perfect reverse. It grabs that 16-bit value from where the stack pointer is pointing, and then it scoots the SP back up by 2, effectively cleaning up after itself and shrinking the stack. Okay, and this brings us right back to our very first question. How does the program find its way home? The answer is the call instruction. Before the CPU ever makes that jump to a subroutine, it automatically performs a push. And what's it pushing? It pushes the current value from the program counter, the exact address it needs to come back to. It's like leaving a perfect digital breadcrumb. And the RET, or return instruction, well, that's how the program follows that breadcrumb trail back. As soon as a subroutine is done, RET tells the CPU to do one thing, perform a pop. It grabs that 2-byte address right off the top of the stack and jams it straight back into the program counter. And just like that, the program picks up right where it left off, without skipping a beat. You know, what's so beautiful about this is the symmetry. Push and call are the putting things on instructions. They both store 2 bytes and move the stack pointer down. Pop and ret are the taking things off instructions. They retrieve 2 bytes and move the pointer back up. It's just a perfectly balanced, elegant system.
So I know this might all seem like really nerdy, low-level stuff, but trust me, this simple mechanism completely revolutionized what was possible with software. Let's talk about why the stack really, really matters. I mean, listen to this quote from the original Intel manual: almost unlimited subroutine nesting. Before this, older CPUs might have had 1 or 2 special registers to save a return address. But because the stack could live in main memory, it could be huge. This meant a function could call another function, which could call another, and another, and another, and the stack would just flawlessly keep track of the entire breadcrumb trail home. And that is the real impact, right there. This one simple mechanism unlocked incredible software complexity. It let programmers write structured, modular code. It was absolutely essential for handling interrupts. Think about it. Every time you even just move your mouse, the CPU has to drop what it's doing, push its entire current state onto the stack, run the mouse code, and then pop everything back to resume exactly where it was. That process, happening thousands of times a second, is what makes modern computing possible. And isn't that just incredible? This fundamental idea, dreamed up almost 50 years ago to solve one simple problem, not getting lost, is still at the absolute heart of every single computer, phone, and smart device you own, including the one you're watching this on right now. It's a testament to truly brilliant design. Which kind of leaves you with one final thought. In today's world of multi-core processors and mind-bogglingly complex software, how has this simple stack of plates evolved to keep up?
You know, deep inside every computer, there's this incredible microscopic drama that unfolds billions of times a second. It's a journey, really, a transformation, and it's the foundation of everything we do with technology. In this explainer, we're going to follow that journey, step by step.
So, have you ever really stopped and wondered how a click of your mouse or a line of code actually makes something happen on screen? How does a piece of software tell a piece of hardware what to do? Well, we're going to follow the hero of that story, a single, humble instruction on its incredible journey right into the heart of the processor.
All right, so to start this journey, we've got to meet our main character. What exactly is an instruction? Well, at its core, it's the most basic, most fundamental command a processor can possibly perform. Think of it kind of like a menu at a restaurant. Every single thing the processor knows how to do, adding numbers, moving data around, you name it, has its own unique number. It's a byte of data called an opcode. So when the CPU sees the code 10000012, it doesn't have to guess. It knows, okay, my job is to add the contents of register D to the accumulator. No ifs, ands, or buts about it. It's a direct command.
And here's something you might not realize. Not all commands are the same size. A really simple command, like add 1 to a register, might just be a single byte. But something more complex, like go grab a value from this specific memory address, needs extra bytes to hold that address. So instructions come in different lengths for different jobs.
Okay, so our little instruction starts its life just sitting there in memory, waiting for its big moment. The very first stage of its journey is getting called up or fetched from memory and pulled into the CPU. This is its call to action.
This whole process has a name, the instruction cycle, and it's basically the fundamental rhythm of every single computer. It's this simple 3-step dance: fetch, decode, and execute. For now, we're focusing on that critical first step, the fetch.
So here's our map for this adventure, a diagram of the classic Intel 8080 processor. And for the fetch, the most important landmark is this little guy right here, the program counter, or PC. Just think of it as the CPU's bookmark. It always holds the memory address of the next instruction it needs to grab, which keeps the whole program running in the right order.
All right, so the CPU has the address from its bookmark. It knows where to go. The next step is actually getting our instruction from the big, wide world of memory into the inner sanctum of the processor itself.
So the call goes out. The CPU puts the memory location from its bookmark onto the address bus. You can imagine it's like shouting an address across a room. The memory controller hears it, finds that exact byte of data, and gets our instruction ready for its big trip.
And then, bam, it's placed onto the data bus. This thing is the main superhighway connecting the CPU to memory. Our instruction travels along this bus, just a stream of electrical pulses, heading straight for the processor's front door. And here we are, the climax of the fetch phase. The instruction has crossed the bus, it's now inside the CPU. But it doesn't just wander around aimlessly. Oh no, it gets sent immediately to a very specific and very important holding area. And there it is, right on our map, its final destination,
the instruction register. You can think of this as the CPU's inbox, or maybe the on-deck circle in baseball. Every single instruction that gets executed must first pass through this exact spot. It's the one and only official entry point for all commands.
And hey, don't just take my word for it. The original 8080 datasheet spells it out perfectly. The first byte of the instruction, that opcode, is transferred directly into this 8-bit register. So the key here is that this isn't just a temporary stop, it's a dedicated piece of hardware with one single job, to hold the current command.
Inside the instruction register, something really profound happens. Our byte of data is no longer just a piece of data sitting in memory. Its status has completely changed. It's now the active, current command in waiting, ready to tell the entire processor what to do next.
Okay, so our instruction is secure inside the instruction register. Great. But what does it actually mean? The CPU has the command, but it doesn't understand it yet. And that brings us to the second step of our cycle: decode.
Let's look back at our map. See how the instruction register is wired directly to the instruction decoder? This thing is basically the CPU's universal translator. It takes that raw 8-bit opcode and translates it into the specific control signals needed to actually carry out the command. So for example, if the decoder sees the opcode for move RM, it's like, okay, we need to read from memory and write to a register, and it flips all the right switches for that. But if it sees the code for add M, it's a totally different story. It fires up the math part of the CPU, the arithmetic logic unit, to do some addition. The decoder is really the brains of the operation here.
So we've fetched the command and we've decoded it. There's only one thing left to do: execute. The translator has done its job, the control signals are sent, data zips between registers, the numbers get crunched, and just like that, the instructions mission is complete. And then, the program counter ticks forward and the whole thing starts all over again.
You know, the decoder also determines how much work is actually required. A simple add-R command, just adding one register to another, takes just one machine cycle. Super quick. But a complex instruction like SHLD, which has to write to 2 separate memory locations, that's way more involved. It requires a full 5 machine cycles to complete.
And this is where it just gets, well, mind-bending. That old 8080 processor could do this a few million times a second. Today's processors, they repeat this entire fetch, decode, execute cycle billions of times every single second. So that entire journey we just followed, from the program counter to the data bus, into that crucial instruction register, through the decoder, and finally to execution, this cycle is the relentless, fundamental heartbeat of all computing.
Think about it. Every time you write an email, play a game, or even just move your mouse, you are kicking off millions of these tiny, lightning-fast journeys. So the real question is, now that you know how it works, what amazing mission are you going to give it next? All right, let's talk about the unsung hero inside every single microprocessor, the one part that makes the whole show run. We're going to pull back the curtain on the CPU's own conductor, the timing and control unit.
You know, at its very core, you can think of a CPU as just a ridiculously fast calculator. It crunches numbers, it compares data. It's the engine that makes all of our digital lives possible.
But that's the million-dollar question, isn't it? An engine is useless without a driver. Something has to be in charge, telling all the different parts what to do, when to do it, and making sure it all happens in perfect sync. So, how does that work?
Well, let's dive right in. The piece of the puzzle we're looking for is the control unit. And honestly, the best way to think about it is as the conductor of a symphony orchestra.
So, take a look at this. This is a functional diagram of the classic Intel 8080 chip. You've got all these different sections, right? You've got the arithmetic logic unit, the ALU. That does all the math. You have registers that hold the data. But see that block right in the middle? Timing and control? That's our conductor. It doesn't play any instruments itself, but it directs every single other part to make sure they all work together to create beautiful music, not just noise.
And hey, don't just take my word for it. This isn't just some made-up analogy. The people who actually designed this stuff at Intel said it themselves. In the official 8080 user's manual, they call the control circuitry the primary functional unit, not the calculator part, not the memory part, the control part. It's that important.
Okay, so to really understand how this conductor keeps the beat, we need to break down how a processor actually experiences time. We're going to zoom in layer by layer from the whole symphony, down to a single, tiny tap of the baton.
So at the very highest level, we have what's called an instruction cycle. This is the whole shebang. It's the total time it takes to do one complete thing, like add number A to number B. From start to finish, that's one instruction cycle.
But it turns out that one big instruction is actually made of smaller steps. Every time the CPU needs to reach outside of itself, say to grab something from memory, that requires what's called a machine cycle. So a single instruction might be made up of 1 or maybe even 5 of these machine cycles.
And we can go even deeper. Each one of those machine cycles is built from even smaller pieces called states. A state is basically the smallest possible chunk of processing activity. We're really getting into the weeds now, with each machine cycle taking about 3 to 5 of these states.
And finally, we hit the bedrock, the absolute most fundamental unit of time in a CPU, the clock period. This is the metronome. It's that constant, unwavering tick-tock that everything else is timed to. Every single state, and therefore every action, is measured by these clock ticks. So here's how it all stacks up. You have one big instruction cycle, which is made of a few machine cycles, which are each made of a few states, which are all timed by those tiny little clock periods. It's this incredibly precise, layered system that lets the control unit manage everything without missing a beat.
Okay, so the control unit has this perfect rhythm. But how does it actually tell the rest of the orchestra what to do? How does it wave its baton? Well, it does it by sending out a bunch of different electrical signals.
These are some of the big ones for the 880. You can think of them as simple shouts from the conductor. Sync basically yells, "Okay, new cycle, everybody get ready." DBIN, which stands for data bus in, is like saying, "My ears are open, send me the data now." WR is just the opposite. It's the CPU announcing it's about to send data out. And then there's ready, which is kind of funny. That's a signal from a slower part, like memory, telling the super fast CPU, "Whoa, hold on a sec, I need a moment to catch up."
And this is what it looks like in action. Now, this timing diagram might seem really complex, but it's just a picture of those signals over time. When a line is high, the signal is on. See that top line, sync? It pulses high right at the beginning to kick things off. Then a little bit later, you see the DBIN line go high, which tells the data bus to send its information over. It's this perfectly timed dance of electricity, and the control unit is the choreographer.
All right, enough theory. We've talked about the rhythm, we've talked about the language of signals. Let's put it all together and watch how one single real instruction makes its way through the system. The instruction we're going to follow is called add M. It's pretty straightforward. It just tells the CPU, hey, go find a number that's stored out in memory, grab it, and add it to the number I'm already holding in this special spot called the accumulator. Simple enough, right?
So how does the 8080 do it? Well, it all starts with machine cycle 1, the fetch. The control unit has to go get the add M instruction itself from memory. That whole process takes 4 clock states, 4 ticks of the metronome. But we're not done. The CPU has the instruction, but it still needs the actual number from memory. So it kicks off machine cycle 2, a memory read. It goes back out to memory to grab the data. This second trip takes another 3 clock states. So let that sink in for a second. That one simple addition required 2 separate machine cycles and a grand total of 7 clock periods to get done. Every single one of those 7 ticks was perfectly orchestrated by the timing and control unit, making sure everything happened in exactly the right order down to the nanosecond.
So now, let's zoom all the way back out. It might seem like we're just talking about an old computer chip from the 70s, but here's the thing. The fundamental ideas, the cycles, the states, the control signals, they are the foundation of every single processor we use today. The conductor is still there, it's just gotten a whole lot faster.
And this chart really drives that point home. The Intel 8080 we've been looking at had a clock that ticked 3 million times a second. Sounds fast, right? Well, just 25 years later, the Pentium 3 was ticking at over 700 million times a second. The basic rhythm of computing, set by the control unit, sped up by a factor of more than 200. It's just incredible.
And that kind of brings us to the big takeaway here. The 8080's conductor kept a beat of 3 million ticks a second. Today's processors have conductors that keep a beat of billions of ticks a second. It's the same dance, just happening at a speed that's almost impossible to wrap your head around. Our entire modern world is built on this foundation of perfect timing, which leaves us with one final, pretty important question. In a world that runs on nanoseconds, what happens when the conductor finally misses a beat?
Have you ever stopped to think about how a computer, with all its different parts, actually manages to work in perfect harmony? It's kind of like a symphony orchestra, right? Every single instrument has to play its part at the exact right moment. Well, in early computers, that harmony was all thanks to a hidden conductor, this web of signals making sure every component played its note perfectly. Today, we're going to pull back the curtain on that conductor inside one of the most influential chips ever made. So let's get right to the heart of the problem. You've got this one central brain, the processor, and it has to talk to memory, a keyboard, a display, you name it. How does it juggle all those conversations at once without all the signals just crashing into each other? How does it tell one part to listen up while another one gets to talk? That is the central challenge we're going to unpack. And our star player for today is the legendary Intel 8080. When this thing came out back in 1974, it was an absolute game changer. The manual itself called it a complete 8-bit parallel central processor unit on a single LSI chip. I mean, this wasn't just another part. It was basically the heart of a computer, our orchestra's conductor, all squeezed onto one tiny piece of silicon. All right, so let's really run with this orchestra idea for a minute. The 808 is our conductor, and it's got this whole ensemble of different components that it has to lead through a flawless performance. Just think about it, the potential for total chaos is huge. The CPU needs to grab an instruction from memory. Then it needs to get a keystroke from the keyboard. And then it's got to send a character over to the display. These are all different chips, and they all have to share the same communication lines without just talking over each other. It's a massive, massive coordination problem. So how did the 8080 actually solve this? Well, it uses a system of, let's call them digital highways, or what engineers call buses. You can just think of these as the dedicated roads that connect every single part of the computer system together. And what's super interesting here is how it breaks down the traffic. You've got 3 main highways. The address bus, that's kind of like a postal service. The CPU sends an address out on it, basically saying, I need to talk to this specific location. It's one-way traffic, always from the CPU out. Then you have the data bus. That's the highway for the actual information, the what. And it's bidirectional, so stuff can go to and from the CPU. But who tells all this traffic when to go and what to do? And that, right there, brings us to the hero of our story, the control bus. This is the absolute key to preventing all that chaos. It's the system that brings order to all the data flying back and forth on those other 2 buses.
Honestly, this is the best way to think about it. The control bus is the traffic cop for the entire system. It's not carrying the addresses or the data itself, nope. Instead, it carries the commands. Things like, hey, memory, get ready to receive this data. Or, okay, keyboard, it's your turn, put your data on the bus now. It's what makes sure that only one device is talking on that shared data bus at any given time.
And you don't have to take my word for it. This quote is pulled straight from the original Intel 8080 manual. The control bus maintains discipline. I just love that phrasing. It's not just about connecting things, it's about discipline, it's about order, it's about control. This is what turns a random pile of parts into a real functioning system. So how does this traffic cop actually give out its orders? It doesn't shout, of course. It speaks a really precise language of electrical signals. So let's take a look at its vocabulary. The 8080 manual spells out these core signals, and they're really the fundamental commands of the whole operation. You've got signals for reading and writing to memory, and also for reading and writing to I/O devices. That's your keyboard or display. Each one tells a specific part of the system what to do, and more importantly, when to do it. Let's break down a couple of the really important ones. First up, we have the write signal, or WR. So when the CPU wants to save some data, it puts the address on the address bus, the data on the data bus, and then it activates this WR signal. This is the command that says, okay, listen up. The data is good to go. Memory location I pointed to, you grab it now. And the opposite of that is read. Now on the 8080, this signal was often called DBIN, which stands for data bus in. So when the CPU needs to get some data, it puts an address out there and then triggers the DBIN signal. And that's the command that says, all right, memory chip, your turn. Put your data on the bus so I can read it.
Okay, and this one is super cool. Interrupt acknowledge, or INTA. So what happens when some external device, like your keyboard, needs the CPU's attention right away? Well, it sends an interrupt request. INTA is the CPU's answer. It's the control signal that basically says, I hear you, I'm stopping what I'm doing for a sec, tell me what you need. This is absolutely essential for making a computer feel responsive.
So let's actually see how these signals all play together in a real-world scenario.
What actually happens when you press a key on your keyboard. This is the anatomy of an interrupt. Okay, so what you have here is this elegant little dance, a digital handshake. And this isn't just theory. This is exactly why your computer feels like it responds instantly. So here's how it goes down. Step 1. The keyboard sends an INT, or interrupt request signal, to the CPU. Step 2. The 8080 is a polite conductor. It finishes whatever little task it's doing. Step 3. The CPU sends back that INTA signal on the control bus. That's the I hear you. And finally, step 4. Responding to that INTS signal, the keyboard puts a special command on the data bus for the CPU to handle. It's just a beautifully coordinated little sequence.
And look, this isn't just a concept. This timing diagram, pulled right out of the manual, shows this dance in microscopic detail. You can literally see the exact moment the INTA signal goes active after the interrupt request comes in. Every single one of these pulses is timed with incredible precision, down to the nanosecond. This is the choreography that the control bus directs, making sure everything happens in perfect, beautiful sync. All right, so we've seen the what and the how, but let's just step back for a second and ask the big question. Why is this so important? Why does this one set of signals matter so much in the grand scheme of things?
Well, because without it, you don't really have a computer. You just have a box of silicon parts that don't know how to talk to each other. Sure, the data bus can carry info, and the address bus can point to places, but it's the control bus that provides the timing, the discipline, the commands that bring it all to life. It's the hidden nervous system that animates the whole machine, turning a pile of parts into a true orchestra.
And really, that's the key thing to take away. Today's processors are unbelievably more complex, but this fundamental idea from the 8080, the need for a central conductor to direct traffic and maintain discipline, is still at the heart of every single computer we use, which kind of leaves us with a final question to chew on. As our systems get more and more complex, more and more parallel, what's the next evolution of this control system even going to look like? Something to think about.
When we talk about the history of computers, we always hear about the big stuff, right? The CPU, the memory, the motherboard. But what about the components hidden away, the ones that are absolutely crucial but never get the spotlight? Well, today we're going to pull back the curtain on one of those unsung heroes, the data buffer. It's the silent gatekeeper of our digital world.
And our story is going to start with a real legend, the Intel 880. This chip, which came out way back in 1974, was a complete 8-bit processor that basically became the brain for the very first personal computers. And tucked away inside its design is the perfect example of why the data buffer is just so important.
So here's our game plan. We'll kick things off with the 8080 itself, then uncover this really big communication problem it had, and you guessed it, we'll see how the data buffer came to the rescue. After that, we'll peek inside the chip, see how it all works, and then connect everything back to the tech we're all using right now.
To really get why this buffer was such a big deal, you have to understand just how revolutionary the 8080 was. This one little chip was an absolute game changer. It was the engine inside machines like the Altera 8800. I mean, that's the computer that got a young Bill Gates and Paul Allen so excited they went off and started Microsoft. It all starts here.
Just try to wrap your head around what was packed into this tiny sliver of silicon in 1974. We're talking 6,000 transistors, an 8-bit CPU that could use its 16-bit address bus to talk to over 65,000 bytes of memory. I mean, for that era, this was a staggering amount of computing power to have in a single component.
But, and there's always a but, right? For all its brain power, the 8080 was, well, electrically fragile. It needed to talk to all this other stuff, memory chips, keyboards, you name it. And that created a really serious problem for the engineers.
Okay, think of it this way. Inside the CPU, everything is perfect. It's a clean, quiet, precisely timed world. The electrical signals are delicate. But the external system bus, that's like a chaotic 8-lane highway during rush hour. You've got all these different devices connected, all making their own electrical noise. If you just plug the delicate CPU straight into that noisy highway, well, it would be a total disaster.
So, that brings us to the million-dollar question. How do you let this brilliant but super sensitive processor talk to the demanding world outside without getting fried or overloaded?
And the answer is this wonderfully elegant bit of engineering we've been talking about, the data buffer. It's the perfect middleman. It's the gatekeeper that stands guard between the CPU's private little world and the chaos of the main system.
And this definition, which is pulled straight from the original Intel datasheet, tells you everything you need to know. The key word here is isolate. Its number one job is to isolate the two buses. It's this temporary holding pen for data that protects the CPU and keeps the information flowing smoothly.
I love this analogy. It's like an airlock on a spaceship. The data buffer lets you safely move things, in this case data, between two totally different environments. You've got the clean, pristine inside of the CPU and the wild, unpredictable system outside. The buffer makes sure neither one messes up the other.
Now, the engineers at Intel knew how vital this was, so they actually built a data buffer right onto the 8080 chip itself. So let's take a look at how this internal gatekeeper actually did its job.
Okay, check this out. This is the official block diagram for the 8080. You can see all the main parts, the registers, the logic unit, and look, right there, connecting the internal bus to the outside world is the data bus buffer. It is literally the only door in or out. All data has to go through it.
So let's break down what makes it tick. First, it's 8-bit, which makes sense because it has to match the CPU's data path. It's also bidirectional, because the CPU needs to both read data from memory and write data to memory. And here's the really clever part. It's 3-state. That means it can be on, off, or, and this is the magic trick, in a high impedance state, which is basically like being electrically invisible. This lets other devices use the bus without the CPU getting in the way.
So that built-in buffer on the 8080 was fantastic for small, simple computers. But you know how it goes. People immediately wanted to build bigger, more powerful systems with tons more memory and devices. And pretty quickly, that little on-chip buffer just wasn't enough. It needed some backup.
And here's exactly why. The data pins on the 8080 could only push out about 1.9 milliamps of current. Now that's just enough to talk to one or maybe two other chips. But if you tried to hook up a whole bunch of memory chips or other devices, the signal would just be too weak to get there. The CPU just didn't have the electrical muscle.
And hey, don't just take my word for it. Intel knew this was a limitation. Their own user manual says it right here in black and white. For a typical system, basically for any serious computer, you needed to add more buffering to handle all the extra memory and I/O devices.
So, a super common fix was to use an external buffer chip, like this Intel 8216 you see here. It acts like a signal booster. It sits right between the 8080 and the rest of the computer, takes that weak little signal from the CPU, and blasts it out powerfully to the whole system. And it does the same thing for signals coming back in, all while keeping everything nicely isolated.
Now you might be sitting there thinking, okay, that's cool history, but what's it got to do with my smartphone or my laptop? Well, turns out the legacy of the data buffer is absolutely everywhere. This isn't just history, it's a fundamental principle of how electronics work.
Because even though our chips today are billions of times more powerful, the basic idea is exactly the same. Modern computers are jam-packed with buffers whose only job is to isolate, strengthen, and control how data moves around. Between your CPU and your RAM, on your graphics card, inside your network port, anytime data has to cross a boundary, you can bet a buffer is there managing the transfer.
It really makes you wonder, doesn't it? The data buffer is just one of these invisible parts that's doing all this heavy lifting behind the scenes. What other unsung heroes are out there, quietly making our entire digital world possible?
You know, when we talk about the history of computing, one chip is just legendary, the Intel 8080. It was the brain in some of the very first personal computers, and it had to solve a problem that, honestly, every computer still deals with today. How do you handle a million things happening at once? So let's dive into one of its most brilliant pieces of engineering, the interrupt system. So let's just get right to the big question. Picture this. It's 1974. You've got keyboards, disk drives, all sorts of devices that need the processor's attention, but at totally random times. How does a CPU from the disco era, with just a few thousand transistors, manage all that chaos without just grinding to a halt? Well, the answer is an incredibly elegant trick. But before we get to that awesome solution, we really need to understand the problem. You see, the most obvious way to handle all these events is also, by far, the most inefficient. This is what we call the brute force approach, or polling. The best way to think about it is this. Imagine the CPU is the driver on a road trip, and all the peripherals are the kids in the backseat. The CPU has to constantly turn around and ask each one, do you need anything yet? How about now? You good? Over and over and over again.
Yeah, as you can probably guess, not a lot of driving gets done that way. The poor CPU spends almost all of its precious cycles just asking questions, which means it can't focus on its real job, actually running your programs.
If your computer worked this way today, everything would feel impossibly slow. It's just a colossal waste of time and energy. So clearly, there had to be a better way. I mean, instead of the CPU constantly nagging every device, what if the devices could just get the CPU's attention only when they actually needed it? This simple idea is the heart of interrupts, and it completely flips the whole model on its head.
And this better way is the interrupt. I love this analogy. Think of it as a polite but firm digital tap on the shoulder.
With the interrupt method, the CPU can just focus entirely on its main program. It's just humming along, doing its thing, until, say, a keyboard has some data to report. That device sends a little signal, that tap on the shoulder, and only then does the CPU pause what it's doing to see what's up. So to put a finer point on it, an interrupt is just a signal that tells the processor, hey, something's happened that needs your immediate attention. The processor is designed to finish the exact instruction it's on, save its place, and then jump over to a special routine to handle whatever happened before coming right back to where it left off. Okay, so that's the beautiful concept, but how did the Intel 8080, a chip with no modern operating system to help it out, actually pull this off? Let's pop the hood and look at the specific tools it used to manage this whole elegant dance. The control system really boils down to a few key parts. First, there's a physical pin on the chip, the INT pin, where devices send their signal. But, and this is crucial, there's an internal switch called the INTE, or Interrupt Enable, flip-flop. And the programmer has total control over this switch using two super simple instructions, EI to turn it on and DI to turn it off. This whole process works like a secret handshake. First, a device sends a signal to the INT pin. The CPU finishes whatever it's doing and then checks its internal INTA switch. If that switch is on, it sends back a special signal of its own, called Interrupt Acknowledge, or INTA. That's the cue for the device to place a special instruction directly onto the data bus for the CPU to grab. And this diagram, it just illustrates that whole exchange perfectly. You don't have to be an electrical engineer to see the story here. You see the INT line go high, then the CPU responds with INTA, and right after that, bam, the device puts that RST instruction on the data bus. It's a perfectly choreographed little dance, all happening in microseconds. Now, remember those EI and DI instructions? These are the programmer's power tools. Let's say you're in the middle of some super delicate, time-sensitive calculation. You can just issue a DI instruction, basically telling the CPU, do not disturb. Once that critical work is done, you issue an EI, and you're opening the door for interrupts again. This kind of control is absolutely essential for writing stable code. So we know the device puts an instruction on the bus, but which one? Well, this is where the 8080's designers came up with a really clever shortcut. This quote from the original manual says it all. Instead of using a normal, kind of bulky 3-byte call instruction, they made a special, super efficient 1-byte version called restart, or RST. Now, in a world where every single byte of memory and every microsecond was precious, this was a huge deal. And here's how it works. The device doesn't have to give the CPU a full complicated memory address. Nope. It just sends an RST instruction with a tiny number from 0 to 7. That number acts like a shortcut, telling the CPU to jump to one of 8 very specific, predefined locations in memory. We call these vectors, and each vector is just the starting point for the little routine that'll handle that specific device. Okay, so this system is brilliant, right? But it does raise a pretty obvious question. The 8080 chip itself only has that one interrupt pin. So what happens if the keyboard and the disk drive both send a signal at the exact same time? How does it decide which one is more important? Well, the answer is the 8080 didn't work alone. Think of it as the captain of a team. It had all these specialized support chips around it that help manage the messy complexity of the real world. So, meet one of the key players, the 8214 Priority Interrupt Control Unit, or PICU. This little chip was basically a traffic cop. It could take interrupt requests from up to 8 different devices, figure out which one had the highest priority based on how it was wired up, and then it would pass a single, orderly interrupt signal to the 8080. It even told the 8080 which RST vector to use. Pretty smart. And the technology just got better from there. The next generation of this chip, the famous Intel 8259, was way more powerful. You could even link them together, allowing a system to manage a whole hierarchy of up to 64 different interrupt sources. This architecture was so good, it was used in PCs for decades. So this whole concept, pioneered in chips like the 8080, isn't just some dusty old piece of history. It is the fundamental principle that makes all of our modern multitasking possible. Every single time you move your mouse, every time a little packet of data arrives over your Wi-Fi, every single tap on your phone's screen, an interrupt is fired. What started back in 1974 with this humble 8-bit processor is still happening, literally billions of times a second, inside the devices we use every single day. So I'll leave you with this thought. This system we've just looked at was a massive breakthrough for managing, maybe 8 devices? The next time you're just casually scrolling on your phone, take a second to think about the incredible high-speed symphony of interrupts happening under the glass, all thanks to a clever trick invented almost 50 years ago. So back in 1974, Intel gives the world this unassuming little piece of silicon, the 8080. But it wasn't just a collection of transistors. No, this thing was a complete 8-bit central processing unit, all on a single chip. And it didn't just power machines, it really did spark a revolution. Let's get into it. You see, this chip was an incredibly powerful brain, capable of crunching numbers and running complex instructions. But think about it. A brain, all by itself, locked away in silence, it's completely useless. To do anything, to run a program, light up a display, read a key press, it had to be able to communicate with the outside world. And that really is the big question for us today. How does a CPU, like the 8080, actually do input and output, what we call I/O, to become the heart of a truly useful computer? Well, the answer is just a brilliant piece of engineering that honestly set the stage for decades to come. Okay, so the first part of the solution is all about building the physical pathways for that communication. The best way to think about it is like a digital highway system, right? A whole network of roads designed specifically to move information around as fast as possible. To build these highways, we've got to look at the physical connections, the pins. You see these 40 little metal legs? They're the literal on-ramps and off-ramps to the 8080's internal world. And Intel's engineers were smart. They dedicated specific sets of these pins to 2 absolutely critical functions. The first of these big highways is the address bus. Now, this is a 16-line, one-way street. Its only job is to shout out an address, kind of like a postal worker calling out a house number. It tells the rest of the system exactly where to find a piece of data or where to send it. This dedicated single-purpose bus brought a whole new level of order compared to some of the earlier, more chaotic designs. And the second highway, that's the data bus. This one's an 8-bit, two-way street. So once the address bus has pointed to the right location, this is the road where the actual data, the instructions, the numbers, the whole shebang, travels back and forth. By completely separating the where from the what, the 8080 created a super clean, logical, and efficient system for communication. So we have our roads, our highways. But without any rules, we'd have absolute chaos, right? Total gridlock. We need a traffic control system to make sure all that data flows smoothly and doesn't collide, and that's where control signals come in. So let's see how this all works together in a simple read operation. First, the CPU puts a specific address onto the address bus. Step 2, it sends out a control signal, that's our traffic light, basically saying, hey, I want to read from here. Third, the device at that address sees the signal and puts the data it has onto the data bus. And finally, the CPU grabs that data from the bus. It's a simple, elegant, and incredibly fast little dance. Now, that control signal we just talked about, it's really a set of 4 main commands that manage all this traffic. The CPU can either read from memory or write to memory. And crucially, it has separate special signals to read from an input/output port or write to one. This distinction between memory and I/O is what gives the 8080 so much of its flexibility. And this flexibility leads us to something really cool, 2 completely different philosophies, 2 distinct strategies that designers could use to manage how the 8080 talked to things like keyboards, printers, you name it. All right, on one hand, you've got what's called isolated I/O. This uses those special I/O signals and dedicated in and out instructions. It keeps the world of memory and the world of I/O completely separate. But then you've got this other really clever technique, memory mapped I/O. This one treats the I/O ports just like they were memory locations. This opens the door to using the CPU's entire range of powerful memory instructions to control devices, not just the basic in and out. And the importance of memory mapped I/O, well, it just can't be overstated. I mean, don't just take my word for it. Intel themselves, in their own manual, said it gives the designer a powerful new instruction set devoted to I/O manipulation. You weren't just moving data anymore. You could do math and logic directly on I/O ports. That opened up a whole new world of possibilities.
This well-designed, really flexible architecture for communication, that was a huge part of the 8080's success. It wasn't just a powerful chip. It was a chip that was easy to build a complete system around, and its ideas, they created a blueprint for the future.
Just look at the evolution to its famous successor, the 8086, the chip that powered the first IBM PC. The basic ideas are identical, just bigger. The data bus doubled from 8 to 16 bits. The address bus grew from 16 to 20 bits, which took memory access from a respectable 64 kilobytes all the way up to a full megabyte. The blueprint was so good, they just scaled it up. At the end of the day, the 8080's design philosophy, those separate highways for addresses and data, all managed by a clear set of traffic signals, it wasn't just a clever solution for its time. It became the foundational blueprint for microprocessor design that would last for decades. And that leaves us with a final thought. Even today, in our world of multi-core gigahertz processors, the fundamental problem is still the same. A brain needs a way to talk to the world. So, as you look at the technology around you, where do you still see the ghost of the 8080's elegant design at work?
All right, today we're going to dive into a real classic of computing history, the Intel 8080 microprocessor. We're going to find out exactly why this game-changing chip had that famous memory limit, just 64 kilobytes. And it all comes down to one key piece of hardware, the address bus.
But first, let's think about a really basic problem. A computer's brain, its processor, is constantly grabbing instructions and data from memory. But how on earth does it find one specific little byte of info among thousands or even millions of other bytes? It's definitely not random. There's a really clever system behind it all.
Okay, so here's our game plan. We'll kick things off with a simple analogy, the CPU's postal service. Then we'll get into the nitty-gritty of the address bus versus the data bus. We'll properly introduce our star, the Intel 8080, and we are going to crack that 64 KB code. After that, we'll see how it all works in the real world and check out the legacy of this 16-bit design. So to really get our heads around how a CPU finds its data, let's start with an analogy. I want you to imagine the entire operation as a super efficient postal service. Okay, so in this city, the CPU, that's your main post office. And the computer's memory? Well, that's every single house and building in the entire town. Every building has its own unique address, and each one can hold a piece of mail, or in our case, a single byte of data.
Now, for this postal service to work at all, it's going to need some roads. In a computer, we call these roads buses. And there are two really important types we need to get straight, the address bus and the data bus.
So what is a bus? It's actually pretty simple. It's just an electrical pathway. Think of it as a set of tiny parallel wires that connect all the different parts of the computer, letting signals and data zip back and forth between them.
The address bus is a one-way street. The CPU sends an address out, kind of like writing the street address on an envelope. It tells memory exactly where to go. But the data bus, that's a two-way street. It carries the actual data, the letter that's inside the envelope. Data can go from the CPU to memory, or it can come from memory back to the CPU.
Check this out. This is a block diagram for the Intel 8080. You see the CPU right there in the middle? Now look for those 16 lines labeled address bus going out. That is our one-way street for addresses. And then you see those 8 lines labeled data bus, the ones with arrows pointing both ways? That's the two-way highway for the actual data. They are totally separate paths, and each one has a very specific job to do.
Okay, now let's talk about our star player, the Intel 8080. This thing was an absolute powerhouse for its time. It was the brain inside some of the very first personal computers like the legendary Altair 8800. If we look at the datasheet, we get the vital stats. It came out in 1974, it was an 8-bit CPU, which means it worked with data in 8-bit chunks, or bytes. And here are the numbers that are absolutely crucial for our story. A 16-line address bus, labeled A0 through A15, and an 8-line data bus. That number, 16, is the key to this whole thing.
So here's the big question. How does a 16-line or 16-bit address bus translate directly into a 64 kilobyte memory limit? Well, it all comes down to the math of possibilities.
All right, this right here. This is the one fundamental fact that explains absolutely everything about that memory limit.
The 8080 CPU has 16 actual physical wires that are just for sending out memory addresses. Each of those wires represents 1 bit, And in the digital world, each line can only be in one of two states, either a low voltage, which we call off, or a 0, or a high voltage, which we call on, or a 1. That's it, on or off.
So how do we figure out the total number of unique addresses the CPU can possibly create? Let's just walk through it. We've got 16 lines. Each one of those lines can be in one of two states. So to find the total number of unique combinations, or addresses, you can make, you just multiply the possibilities. So it's 2 times 2 times 2. You do that 16 times. In math, we just write that as 2 to the power of 16.
And 2 to the power of 16 equals 65,536. That's it. That is the total number of unique addresses the Intel 8080 16-bit address bus can ever generate. It covers every combination, from an address of all zeros to an address of all ones. And hey, don't just take my word for it. This is pulled straight from the original Intel 8080 user's manual. It states right there, clear as day, that the 8080 can directly address up to 65,536 bytes of memory. Each unique address points to one single byte. So where does 64 kilobytes come from? Well, in computing, a kilobyte isn't 1,000 bytes, it's actually 1,024. And if you take our big number, 65,536, and divide it by 1,024, you get exactly 64. And there it is, the famous 64 KB memory limit. It wasn't some random number they chose. It was a direct consequence of the physics, of the math, of having a 16-bit address bus.
Okay, so we've totally cracked the math, but what does this actually look like on the hardware? In practice, how does the CPU use these addresses to actually read and write data? Have a look at this memory interface diagram. You can see the 16 address lines running from the CPU over to the memory chips. The CPU puts a specific 16-bit address onto that bus, and that address acts like a key, unlocking one specific byte-sized location in memory. Then the 8-bit data bus is used to either grab the byte from that location or put a new one in its place.
That 64 KB limit really defined an entire era of computing. It forced all those early software developers to become absolute masters of efficiency. But, of course, technology never stands still, and the legacy of the 8080's design shows us just how important the width of that address bus really is. Just a few years later, Intel released the 8086. And just look at the difference here. They expanded the address bus from 16 bits to 20 bits. And just those 4 extra lines, they increased the addressable memory from 64 kilobytes all the way up to 1 times megabyte. That is a 16-fold increase.
And this is the fundamental lesson here. Because the math is all based on powers of 2, every single time you add just one more line to the address bus, you double the total amount of memory the CPU can talk to. This exponential growth is exactly why the address bus width became one of the most important specs in processor evolution.
And that brings us to today. We've gone from 16 bits to 32 bits, and now to the 64-bit processors that are in nearly every modern computer. So I'll leave you with a final question to chew on. If 16 bits gave us 64 kilobytes, how much memory can today's 64-bit processors theoretically handle? The answer is mind-bogglingly huge, and it really shows you just how far we've come from the 64 KB world of the Intel 8080. Thanks for joining this explainer.
Have you ever stopped to think about how a computer, with all its different parts, actually manages to work in perfect harmony? It's kind of like a symphony orchestra, right? Every single instrument has to play its part at the exact right moment. Well, in early computers, that harmony was all thanks to a hidden conductor, this web of signals making sure every component played its note perfectly. Today, we're going to pull back the curtain on that conductor inside one of the most influential chips ever made. So let's get right to the heart of the problem. You've got this one central brain, the processor, and it has to talk to memory, a keyboard, a display, you name it. How does it juggle all those conversations at once without all the signals just crashing into each other? How does it tell one part to listen up while another one gets to talk? That is the central challenge we're going to unpack. And our star player for today is the legendary Intel 8080. When this thing came out back in 1974, it was an absolute game changer. The manual itself called it a complete 8-bit parallel central processor unit on a single LSI chip. I mean, this wasn't just another part. It was basically the heart of a computer, our orchestra's conductor, all squeezed onto one tiny piece of silicon. All right, so let's really run with this orchestra idea for a minute. The 808 is our conductor, and it's got this whole ensemble of different components that it has to lead through a flawless performance.
Just think about it, the potential for total chaos is huge. The CPU needs to grab an instruction from memory. Then it needs to get a keystroke from the keyboard. And then it's got to send a character over to the display. These are all different chips, and they all have to share the same communication lines without just talking over each other. It's a massive, massive coordination problem. So how did the 8080 actually solve this? Well, it uses a system of, let's call them digital highways, or what engineers call buses. You can just think of these as the dedicated roads that connect every single part of the computer system together. And what's super interesting here is how it breaks down the traffic. You've got 3 main highways. The address bus, that's kind of like a postal service. The CPU sends an address out on it, basically saying, I need to talk to this specific location. It's one-way traffic, always from the CPU out. Then you have the data bus. That's the highway for the actual information, the what. And it's bidirectional, so stuff can go to and from the CPU. But who tells all this traffic when to go and what to do? And that, right there, brings us to the hero of our story, the control bus. This is the absolute key to preventing all that chaos. It's the system that brings order to all the data flying back and forth on those other 2 buses.
Honestly, this is the best way to think about it. The control bus is the traffic cop for the entire system. It's not carrying the addresses or the data itself, nope. Instead, it carries the commands. Things like, hey, memory, get ready to receive this data. Or, okay, keyboard, it's your turn, put your data on the bus now. It's what makes sure that only one device is talking on that shared data bus at any given time.
And you don't have to take my word for it. This quote is pulled straight from the original Intel 8080 manual. The control bus maintains discipline. I just love that phrasing. It's not just about connecting things, it's about discipline, it's about order, it's about control. This is what turns a random pile of parts into a real functioning system. So how does this traffic cop actually give out its orders? It doesn't shout, of course. It speaks a really precise language of electrical signals. So let's take a look at its vocabulary. The 8080 manual spells out these core signals, and they're really the fundamental commands of the whole operation. You've got signals for reading and writing to memory, and also for reading and writing to I/O devices. That's your keyboard or display. Each one tells a specific part of the system what to do, and more importantly, when to do it. Let's break down a couple of the really important ones. First up, we have the write signal, or WR. So when the CPU wants to save some data, it puts the address on the address bus, the data on the data bus, and then it activates this WR signal. This is the command that says, okay, listen up. The data is good to go. Memory location I pointed to, you grab it now. And the opposite of that is read. Now, on the 8080, this signal was often called DBIN, which stands for Data Bus In. So when the CPU needs to get some data, it puts an address out there and then triggers the DBIN signal. And that's the command that says, all right, memory chip, your turn. Put your data on the bus so I can read it.
Okay, and this one is super cool. Interrupt Acknowledge, or INTA. So what happens when some external device, like your keyboard, needs the CPU's attention right away? Well, it sends an interrupt request. INTA is the CPU's answer. It's the control signal that basically says, I hear you, I'm stopping what I'm doing for a sec, tell me what you need. This is absolutely essential for making a computer feel responsive.
So let's actually see how these signals all play together in a real-world scenario. What actually happens when you press a key on your keyboard? This is the anatomy of an interrupt. Okay, so what you have here is this elegant little dance, a digital handshake. And this isn't just theory. This is exactly why your computer feels like it responds instantly. So here's how it goes down. Step 1, the keyboard sends an INT, or interrupt request signal, to the CPU. Step 2, the 8080 is a polite conductor. It finishes whatever little task it's doing. Step 3, the CPU sends back that INTA signal on the control bus. That's the I hear you. And finally, step 4, responding to that INTS signal, the keyboard puts a special command on the data bus for the CPU to handle. It's just a beautifully coordinated little sequence. And look, this isn't just a concept. This timing diagram, pulled right out of the manual, shows this dance in microscopic detail. You can literally see the exact moment the INTA signal goes active after the interrupt request comes in. Every single one of these pulses is timed with incredible precision, down to the nanosecond. This is the choreography that the control bus directs, making sure everything happens in perfect, beautiful sync. All right, so we've seen the what and the how, but let's just step back for a second and ask the big question. Why is this so important? Why does this one set of signals matter so much in the grand scheme of things? Well, because without it, you don't really have a computer. You just have a box of silicon parts that don't know how to talk to each other. Sure, the data bus can carry info, and the address bus can point to places, but it's the control bus that provides the timing, the discipline, the commands that bring it all to life. It's the hidden nervous system that animates the whole machine, turning a pile of parts into a true orchestra. And really, that's the key thing to take away. Today's processors are unbelievably more complex, but this fundamental idea from the 8080, the need for a central conductor to direct traffic and maintain discipline, is still at the heart of every single computer we use, which kind of leaves us with a final question to chew on. As our systems get more and more complex, more and more parallel, what's the next evolution of this control system even going to look like? Something to think about.